Okay, let's get started. Looks like everybody's got a laptop. That's good. I've been excited all weekend for today's class meeting that we get to go over StormCAD today. Now, part of the reason why I feel so strongly about teaching you these software applications when I can is that's how I got my first job. After I graduated, it was a very different environment than you'll likely be entering, where now there's probably 3 engineering job openings for every person who graduates, and every week I'm getting people begging me, hey, do you have graduates that you can apply for, that you can have apply for this position? There's just like so much need for engineering now. That wasn't the case when I graduated. There was really a lot of competition, and one way that I was just able to fortunately find a job was I knew how to use HY8. And this firm that I applied to knew that they had a new project coming on where they needed someone to be able to use HY8. Even though as a fresh graduate, I had just a little bit of experience with it that I learned in school, and so that's ultimately a big part of why I ended up getting hired. So, obviously the purpose of your education in engineering is to learn like the facts and the background and the knowledge that will help you to be successful, but it's also to get the skills and the mindset of an engineer. And so I think that StormCAD is something that, it's a valuable software package that you're going to be able to put onto your resume and say that you're familiar with it. I mean, you won't be an expert, but you'll be familiar with it so that, with a little bit of training, you can be very useful to a company. So that's why I'm excited to show this to you. Plus, I think it's an interesting program once you get around the nonsense of getting it activated and running the Connect client. But just to look at some announcements here. So you've just turned in homework 2 online, and I didn't intentionally omit the FAA equation from the slides that I shared with you earlier, but just occasionally this semester there's going to be some things that you have to go to the textbook to learn. And especially if you look through that list of terminology, the concepts and terms, there's some of them that we may not even mention in class, but I still think it's important for you to know. So, like the FAA equation is in the table in chapter 15. It's just pretty similar to the rest of them, where it's like an empirical formula that you substitute values into. So there won't be too many situations like that, but they will pop up from time to time. I got one question that was about how do you determine the slope, because remember that the slope of the surface is a parameter that you have to use for some of those equations. And if you used Google Earth and hover your cursor over the parking lot, then you'll notice that it tells you the estimated elevation wherever your cursor is. And so that would be one way to estimate the slope of the pavement, is to hover your cursor in one location, get the elevation, move a known distance, find out the new elevation, and then calculate the slope from that. There's other ways of estimating in other programs, but that's one of the approaches that you could use for the equations where you need the slope. All right, so homework number 3 I have right here. I'll hand out to you before you leave. It's due a week from today, and it's going to require you to use StormCAD, which we're going over today, and then we're going to do some stormwater detention and pond sizing work on Wednesday and Friday of this week. Any questions before we get started with StormCAD? Okay, here is an outline of the workflow, and I've handed this slide out to you in case you want to take some notes on it. This isn't included in the lecture notes. That's the PDF. I just put this together today after I was working through the demo, just so that you could remember what are the steps that ought to be followed when you're setting up a model. And here is the system that we're going to size. And we already looked at this same system when we were doing the spreadsheet problem. So we're going to see if we get a similar answer as we did with that spreadsheet. There's 2 basins, a smaller basin and a larger basin. You can see that we've got 2 pipes in our system, a catch basin where all of the water from the smaller basin goes into catch basin 1, and then the water goes through pipe A, and so water is entering catch basin 2 from 2 locations. Water's coming into that. It's like basically a concrete vault with a grate at the top that rainwater flows in from the top from this surface flow, and then there's an inflow pipe to that concrete vault and an outflow pipe to that concrete vault. So you can see that the slopes and the lengths of each of those pipes are given, but we don't know what diameter is required in order to convey all of the flow. And so the example that we're going to look at is we're going to see what pipe size would be required in order to make it big enough to capture the 10-year storm. There's a couple of assumptions you need to be aware of, and one of them is we're going to assume that this grate that we put in can capture all of the flow that comes off of the parking lot, just for simplicity's sake. But I want you to be aware that that may not always be the case, because there's different grate sizes and lengths. And so we're going to assume that this is like in a low point of the watershed, and all of the water that goes to it is ultimately going to get into that catch basin. In reality, if a grate is along a road, and let's say that the street is on a slope, the water may flow over the grate and only a fraction of it would go down through the grate and into the vault, and some of it would continue onward. So inlets aren't always 100% efficient at intercepting the flow, but we're going to assume and set it up so that they are 100% efficient. We also have ground elevation and invert elevations that we'll need for this example. The slope that's specified here, you can't specify slope directly in StormCAD. Instead, it determines the slope based on the length that you tell it and the elevation of the pipe at each end. So we won't. You'll notice there's no place we tell it the pipe slope, but rather it gets that from the invert elevation. 10-year storm. Here is a precipitation depth table. These are not intensities. These are depths. And so there's a couple of different ways to specify the storm data in StormCAD, and we'll look at 2 of those methods today. And the one that we'll ultimately use for our problem will rely on these depths. Okay, so let's go ahead and start up StormCAD, and I think I'll probably need to get the Connect client logged in and running if it's not already. Looks like it remembered me. I don't have to log in again. That's a plus. Never sure how to get rid of that thing. All right, so we're going to create a new hydraulic model. If you're at this same screen, just click on the middle button there. And it's probably going to prompt us to say, do we want to track changes effectively? And we'll say no to that. We don't necessarily need all of our adjustments tracked with this model, so no. All right, so if you look at the workflow, it says first thing is to draw the elements. And so what we're going to try and depict is a schematic that summarizes this network. 2 catch basins followed by an outfall. And so here is the button layout that you use to begin drawing. See the layout tab, we're on the home and then layout. And if you move the cursor down into the drawing window, it's going to start off with this circular symbol, which is for a manhole. And we don't want to drop a manhole, we want to drop a catch basin. So I right-clicked to bring up this menu. So moving the cursor around, right-click, catch basin, and then just drop 1, 2 catch basins, and then right-click again and choose Outfall. Left click and then escape. So we should end up with 2 of these squares connected to a triangle. So it's catch basin 1, catch basin 2, outlet 1. You'll notice that it's automatically named the pipe Conduit 1 and Conduit 2, which is fine for now. We're going to update that and adjust it. Any questions so far on what we've done? This is a top view. that we're looking at. This isn't a side view, so it doesn't really matter where you click because we're going to go in and tell it the length of these pipes. It has a scaling system. If you notice down at the bottom, it has X and Y coordinates. So if you had a picture in the background, you could drop these catch basins at the location intended on a map. And so you could make a scaled system based on a drawing in the background. But for this first example, we'll just override any length that it is inferring from where we clicked. We just mean for this to be a schematic. Any questions before we move on? Okay, so we've drawn the elements. Let's move on to part 2 of the workflow, conduit properties. And there's a couple of different ways to change the properties. One is if you use the select button. So now you've just got this pointer and you double click on something. So if you double click on the pipe, it will bring up its properties this way. It has a lot of properties. It's a very long list, most of them not applicable yet because we haven't calculated any hydraulic scenario. But it's more efficient if we edit all of the properties at once rather than on an individual one-by-one basis. And so instead of just like double clicking and bringing up its properties for that individual pipe, it's better to open up the flex tables. And so you'll notice this button across the top with the drop-down arrow. If we choose the conduit flex table, it brings up this menu and it has both of the pipes. So now we could edit the properties of both of them. So for instance, changing the label from conduit 1, I could label that pipe A, which is the label that was on the drawing. And as soon as I type enter, it updates the annotation that exists on that sketch already. And so then the other one I'm going to call pipe B to be consistent with the description that was on this sketch. Pipe A, pipe B. So likewise, we're going to be able to adjust the length of the pipe. So if we scroll over, right now it thinks the length of pipe A is 184 feet. And that's just based on like where I clicked in the window. So that's not the right length. What I need to do is tell it to not look at that and use a user-defined length. And so there's this checkbox here that says has user-defined length. I'm going to turn that on, and you'll notice that it's going from yellow to white in the length field. So that now I can put in my own known lengths of 450 feet for pipe A, and 600 feet for pipe B. So that we've done that through the user-defined lengths. All right. You'll notice it has the section type is circular. It's got a default Manning's N value of 0.013, which would be for a relatively smooth concrete. I think that the example suggests that the N values are 0.014. So let me make that adjustment. So the N value, I'm going to just change it to 0.014 for both of those. And instead of 12-inch diameter, I already know that that's a little bit small for these areas. Let's just change it to 15 inches for both of them and see how that does. All right, so keep scrolling to the side. Okay, I think that's all we need to have so far. Once we put in a characteristics of the watershed that goes to these catch basins, and once we click the compute button, a lot of these like flow, velocity, depth, that stuff will fill in once we've calculated the scenario. But so far we've just told it the physical characteristics of the pipe. Any questions before we move on to the catch basin properties? Okay, so we've defined the conduit, which is just another word for pipe. Now let's go into the flex table for the catch basin. Just like before, I could, if I wanted, I could just double click and that would bring up the properties of one catch basin. But it's better, I think, especially for a complicated network, if you bring up the flex table and see it all in tabular form. All right, so I think the labeling that I had for the catch basins was I just called it CB1 with no dash. So CB1 and CB2, that was pretty close to begin with. Ground elevation. Ground elevation doesn't go into the hydraulic calculations, but it will give you warning messages if the ground elevation is too close to the top of the pipe. So it's useful to have the ground elevation in there just so that you avoid the mistakes. And on the handout I gave you, it says that the ground elevation at catch basin 1 is 100 feet, and at catch basin 2 it's 95.5 feet. And then we also have the invert elevation. That is the bottom of the pipe that's coming in or out of the catch basin. It's going to set the pipe elevation equal to the invert. Invert elevation means it's this concrete vault where the top of the vault is at the roadway surface, the bottom of the vault is some distance below that. So the invert elevation to catch basin 1 is 95, and the invert for catch basin 2 is 90.5. All right. I don't think that you have inlet location on yours. If you scroll over to the side, does yours say inlet location? No. Okay. So the way that you add that is this yellow button for edit here. Scroll down on the list on the left until you find inlet location. And once you've got it, click on this add button, the one on the top, the single arrow to the right. And then what that'll do is it'll add that column to what you view in the catch basin table. And the reason why we need to have that inlet location on our list is we're going to tell this that this inlet is in a sag, and that's a way of forcing it to assume that all of the water in the assigned watershed goes into the catch basin. If it's in a sag, then that just means it's like at the bottom of a low point in the watershed, and so all of the water will get into that grate. This program has so much sophistication that obviously we can't get into every function in a 50-minute class demo. And part of the functionality it can have is calculating how much interception there is as the water's flowing over the top of a grate. It'll be able to calculate based on the shape of the grate, the width. There's these standardized patterns that even have different angles of the openings. It can calculate how much of the water is going to get in there. But just for simplicity's sake, we want it to assume that all of the water gets into that, and so set the inlet location to sag. Has everybody done that? Okay, so once you got that specified, we're done with these catch basin properties. We can close this menu. Next, we're going to define the outfall properties, and so open up the flex table to the outfall, and I think we called this, instead of O1, it was OF1. Not much of a difference, but let's give it the ground elevation, which from the table on the handout says it's 93.1. The invert, the bottom of that junction is 88.1. And I don't think there's anything else that we specify for the outfall. Okay, so we specified that. You can close it. Okay, we haven't yet defined any catchments. You'll notice that step 5 on this workflow is the catchment properties. We need to draw the basins, the actual watershed. So if we go back to the sketch to look at it, we've got this watershed is 1.5 acres, this one is 3.2. So this is just a schematic that we're putting together, and we need to represent those two basins. And where we do that is here in the Layout tab. We've been mostly in the Home tab so far, but switch to the Layout tab. And here's this green button at the top, the Catchment button. So click on that, and when you bring your cursor down into the drawing window, you can tell that now you're going to start sketching out just a symbolic representation of the catchment. Remember, this isn't a scaled map that we have in the background. If you did have like a design drawing of the project area, you could trace the boundaries of the catchment, and it would calculate the area that way. But in the same way that we manually told it what was the length of the pipe, we're going to do the same thing here with the area of the catchment. So I just need to trace some shape so that it knows. I'm going to double click, right click, done. You just trace some shape. It doesn't really matter where it is. It doesn't even have to be on top of the basin necessarily, because we're going to link it. We're going to tell it the relationship of which catchments go into which catch basins. So just to illustrate that, here I'll draw this one above, but I'm going to define that the water from this watershed goes into catch basin 1. The water from this catchment goes into catch basin 2. So we've drawn the catchments, and now let's go into the flex table for it. Does anybody need help with drawing the catchment? Sometimes that can be tricky because of the right click at the end to make it done. Anybody need a moment? Some assistance? Okay. So assuming that we've got all this drawn up to now, then in the Home tab, in the Flex tables, open up the Catchment Flex table. And this is where we put in all of the watershed properties. So if we look at what we had in this original drawing, we didn't have a specific name for either of the catchments, so we'll just go with the default. But we know the area in acres, the time of concentration in minutes, and the C value. So let's just translate that over. First, the area in acres. So it says here a user-defined area. So 1.5 acres is for the first area, and it was 3.2 acres for the second. The runoff coefficient, that's the C value, so 0.075 and 0.55. Now look at the units for time of concentration. It says hours in that table. What units do you have in the example? Minutes. So, I mean, it's not like rocket science to make the conversion between minutes and hours, but if you had like 3 or 4 dozen catchments, it would be more convenient just to be able to type it in as minutes rather than have to do the calculations. And so you can change the units that it's using. So here on time of concentration, put your cursor on that column heading and right click and units and formatting. So right now it's on hours. Let's change it to min, which means minutes. And we don't need it to have like 3 decimals afterwards. So we could just have like 1 decimal. Okay. So now I can type in the minutes. And so I had that it was 10 minutes for the smaller watershed and a time of concentration of 30 minutes for the larger watershed. Okay, so in the mind of this model, it still doesn't know which catchments are connected to what catch basins. We haven't yet defined that linkage, even though like it's closest to, like this was drawn on top of catch basin 1. It doesn't assume based on that that's where the water's going. You have to tell it. And that's what this outflow element column is for. So if you click in the outflow element, it has this ellipsis, the ... So click on that, and now it's saying, okay, so tell me, where does the water go? Select it on the drawing. So it's asking you to click on one of the catch basins. So I'm going to click on catch basin 1, and so now it knows that the outflow element for catchment 1 is catch basin 1. So the same thing for catchment 2. I click down in that field, click on the ellipsis, and then it's highlighted here in red. It's asking, where does the water go from this watershed? And I say it goes into catch basin 2. Now, that dashed line kind of is our visual representation. The model knows where the water will be entering the pipe network. Okay? Think about, this is using the rational method. Q equals CIA. What haven't we told the program yet in the rational method? It's going to calculate Q, but what didn't we tell it? CIA. What doesn't it know yet? The intensity, right. It knows C and it knows A because we just put those in here. These time of concentration, it's going to use that in determining the intensity, but it still needs to know what do the rainfall patterns look like in this area. So we're going to define as our next step here, step 6, storm data definition. Okay, so go here to storm data and the storm data option. So click on that. It's going to bring up a dialog box of a couple, well, there's lots of options here. The two I want to show you today is, first of all, a user-defined IDF table. So if I do new user-defined IDF table, it opens up this. You'll notice it created an entry down here. But let me add a return period. Let's say that I want to put in the 10-year storm in here. And so now I'm going to add durations. And let's say, for instance, that I know the storm duration for the 5-minute duration of the storm. Add the duration with the 10-minute, 15, 30, and 60. I wonder if this range would have made it so that I could do that all at once. But all right, so now what I need to tell it is I need to tell it what is the intensity of the storm for the 5, 10, 15, 30, 60. This is what you'll be doing for the homework. And the data is on this handout I'm going to give you. So for example, the 5-year storm, 10-year storm, 5-minute duration has an intensity of 5.4 inches per hour. 4.2, 3.2, 2.3, and 1.4. So this is the curve for the 10-year storm that tells you, if you know the return period, what will be the intensity of the storm. So we could tell StormCAD to use this as how it's going to find out the intensity. Is there anything I need to show again for this user-defined IDF table? Anything I went too quick through I could show again?
Where did you get your 10-year storm data?
Oh, it's on the homework handout I'm going to give you. So it's nothing that you've got in front of you.
Okay.
Yeah, just mimic what I've got for now. But I will give you on the assignment what storm you should use for the design problem. So Hydro 35 is another option. So let's create a Hydro 35 storm to use. So here, this new Hydro 35. What it does is, if you put in the 2-year and the 100-year storm, and if you put in the 5, 15, and 60-minute duration, then it'll interpolate everything in between. It's going to interpolate the 5, 10, 25, 50, and it's going to interpolate durations like 10 minutes, 30 minutes. There's just like these typical scaling relationships that it will use. So on the handout I gave you, this is the third slide where it has, this is the depth for the 2-year, 5-minute is 0.419. Now the 15-minute duration, 2-year, 0.799. Boy, that is a little bit blurry. The 60-minute duration is 1.31. Okay, now we'll put in the 100-year storm. The depth for the 5-minute is 0.755. For the 15-minute is 1.41. And for the 60-minute is 2.73. So you'll notice it has this kind of scaled, extrapolated IDF curve. So we've created 2 different storms that we could have the program look at. Like when we say compute, we're going to tell it what storm to assume is coming through our network. So we could size the storm for like a we could size the pipes for a 10-year storm, and then we could say, well, let's see how it does when it's just a 2-year storm. We could run a different simulation after we've finalized our design. Okay, so we've defined the storm data. Any questions before we move on to step 7, which is compute? Okay, so we close that. This green button, compute. Just click the green button. Fingers crossed we don't get a bunch of error messages. Let's see, there is a concern. Oh, we didn't tell it the storm to use. That is a big concern, yeah. So back to the storm data tab. We defined the storm events, but we didn't assign which one it should look at. Remember, there was lots of options, so I forgot to tell it whether to use the user-defined IDF table or whether to use Hydro 35. So if you click on Global Storm Events, the Global Storm Event drop-down box, we can either use this user-defined IDF table or the storm data that was from the Hydro 35. Let's do the Hydro 35 10-year storm instead of that user-defined. So Hydro 35 10-year storm, close that. All right, now when we compute, hopefully we won't get a red exclamation mark here. I think it will have a concern based on the ground cover, but it won't be an error message. Convergence was achieved. We like that. That means that it finished its calculations. It thinks it knows what the depths are going to be. Convergence was achieved. So the only thing that comes up on the picture is just the flow direction. But obviously we need to know more than that. Let's look at these messages here. One or more conduits are operating under pressure. That is a sign that one of the pipes is too small, that it's undersized. Conduit discharge is above design discharge. That's again another thing that's telling us it's too small. And then a warning here, conduit does not meet minimum slope constraint. So the program has guidelines of what would be the shallowest slope that would be acceptable. So, you know, some towns really don't have a lot of options. They can't make the pipes any steeper simply because they're flat towns and the river's at a certain elevation. Let's get into the flex tables and see what data we can get out of there. Any questions before we do? Okay, so open up the conduit flex table.
Does it matter if we have different notifications than what you do?
I don't know. What does your notification say?
So I've got a minimum cover constraint as well.
Yeah, that's not the end of the world.
I got one that says one or more elements is flooding during this time.
Okay.
Yes.
One or more elements is flooding. So I think those all probably mean the same thing, that the pipe is too small. So hopefully when we make the pipe B is too small, just to reveal that's our problem pipe is too small. Once we make it bigger, I think those error messages will go away. The minimum cover won't though. The minimum cover thing is looking at the elevation. So you know how I said the ground elevation here, the invert elevation is there? It is thinking there's not enough soil on top of the pipe. It's too close to the surface. So we would maybe have to rethink what elevations we use for the inverts. But for getting a sense for how the model operates, I don't think any of those errors are fatal errors for now. So we'll just move on. Open up the conduit table. And if you scroll to the side, what you're going to see is some of those fields that were blank before in yellow now have flows calculated, velocities. I think I may have a typo somewhere. I'm expecting more flow for that first pipe. Pipe A should have more flow than that, I would have expected. But you'll notice that pipe B is undersized. Look at the capacity of the pipe compared to the flow. So this is saying it calculated that there's 5.45 CFS that's entering that pipe, but it only has a capacity of 3.79. So you could see where that would be a problem. Josie, do you have a question?
Yeah, my flows are 5.66 and 8.4.
Okay. The only difference would be in like your catchment. Let's open up the catchment and see if I've maybe typed in, look at my C value, 0.075. is supposed to be 0.75. Let me recalculate. All right, I'll open up my conduit table.
My message now about flooding.
Okay, so let's look. So pipe A is at 94% capacity. So pipe A is sized okay, but pipe B is it's way over capacity. Do you see this flow to design capacity ratio? That kind of gives you a sense for whether the pipe is too small or too big. There's lots of different ways to see it. You just compare the flow to the capacity and see that pipe A is all right, pipe B is too small. Could we make pipe A smaller? Like it's 15 inches right now. What if I tried to go down to 12 inches? Well, if I went to 12 inches, it's already calculating that I would be at 171% capacity. See how that changed, this ratio of flow to design capacity? So I'll put that back at 15. 12 would be too small. I won't be able to immediately see the new implications. Like if I go from 15 to 18, it didn't automatically update this because I need to compute it again. So push the green arrow, and you can even leave the flex table open. Compute. Okay, still not big enough. It's not as bad as it was, and some of our error messages went away. Like that error message about the flooding, element is flooded. We don't see that anymore. It is under pressure, but it's not flooded. I think what flooded must mean is that there's so much water there that it rises to the surface, that there isn't enough elevation difference for the pipe to be pressurized exclusively. Okay, so pipe B still needs to be bigger. 18 wasn't large enough. Let's try 24 inches and calculate again. All right, I think that's going to do it. We're at 94% for pipe A and 63% for pipe B. Now, if there was a 22-inch pipe available for us to buy, we could try that. But in this case, it's the 24-inch pipe. Like if we just had 15, 18, and 24, 36, then we'd be stuck using this 24. It's as close as we can get to optimal. Okay, so that was step 7, compute. Any questions before we move on to annotate? Do you know what the word annotate means?
Add labels.
That's right. It's adding labels to the drawing. It already has a couple of labels. It's got the word pipe A. It's got the labels for CB and CM, but let's say we want more than that. So in the homework, I ask you to annotate the catch basin label. We've already got that, CB1. The outfall label, OF1. Okay, that's good. And for the conduit, we want the conduit label. That's already there. But now the length. We want that to be in the drawing. So over here on the element symbology window, click the plus, and then right-click on the word conduit, and new annotation. So again, what we're doing is over here on the left side of the screen, right-click on the word conduit, new annotation, and the field name, scroll down to length user defined. Okay. And then for the prefix, I'm going to put L space equals, and let's see if I click apply what it does. Look, it's right on top of the pipe. That's not real convenient. You can't see it very well. So this offset will push it down. So for the Y offset, do -6 and apply. And that brings it down off the center of the pipe to a better location. And maybe I want to put an extra space after the equal sign too. There, I like the way that looks a little bit better. You can still adjust the location of these annotations, but this initial offset can get things so it's not just all jammed on top of itself. Okay, so we've got the length. What about the diameter? So click OK. Right-click on the word conduit. new annotation. From this drop-down box, choose diameter. There it is. And D space equals space. Now, I'm going to have to do a vertical offset. Let me do the y offset of -12 and apply. Okay, that seems all right. So we've got the diameter of each of those. I'm going to do another annotation that is the flow. New annotation. And scroll down the list to flow. We'll have Q space equals space, negative offset of -18, apply. There it is for the Q. Do another annotation, new annotation. The last one we'll have for our conduit is like an indication of the percent capacity. So the field name to scroll down to is flow divided by flow capacity. Flow divided by capacity, this one. And then for the prefix, I'm just going to call it percent. Where's my percent? There it is. Percent capacity equals. And I guess, where am I at for my offsets? -18?
You just said 18.
24. All right. Okay, so the pipes are annotated. Let's also annotate the catchments. So right-click on the catchment, new annotation. Let's say I want it to have the area. So drop-down box, area, user-defined. So A equals, and I probably ought to do an offset of, let's try a -15, see where that ends up. Fine. Okay, and then also the C value. Annotation. Runoff coefficient rational. So then I'll do C equals, and maybe -21. Okay. And once I get back to just my normal cursor, so up here, the select button, I can select these labels and move them around either as a group, like you can see now that I'm moving it as a group, or I could just pick one of them individually and move that one. Yeah, there it is. So if I felt like one of them was like right on the border where it was inconvenient, I could make adjustments just to improve the visual appeal of what I'm working on. Maybe some of you, it's not filling up the screen like mine. Like maybe some of you, it looks like that. You're probably already familiar with a similar function here, zoom extents, maybe from AutoCAD or MicroStation. If you click on that, it's going to fill up the whole window. Let me show you how to do a print of this. The last thing is, if we go over here to File, Print, and leave it on Fit to Page. Let's do Page Setup. Just based on the shape of what I've done, I think it would be better as a landscape instead of portrait, because I made it kind of long. It was more long than it was tall. So landscape would be better. And these margins, I'm not actually going to print it. I'm just going to make a PDF, so I might as well make the margins a bit smaller, 1/2 inch. Okay, OK. And then print preview. Let's see what that looks like. All right. So here's what my print preview looks like, and I'm going to do File, Print, ... and let's see, Microsoft Print to PDF. I want to make a PDF out of this. So I'm going to click Print, and it may give me a location. Where do I want to save it? I'll just put it on my my jump drive here, StormCAD example. And the advantage of having a PDF is like if I just did print screen, like if I'm going to push the print screen button right now, print screen. And if I paste that into a Word document, like that screenshot, it's not going to look very good, especially if I try zooming in. It's blurry, and the lettering is blocky. Do you see how that, just doesn't look that great? It doesn't have the same resolution as if I now take a look at that PDF file that I just created, StormCAD example. The text is vector rather than raster, which means that you could zoom in some infinite amount and it's still going to be sharp. Be even sharper if I opened up in Adobe Acrobat rather than the internet browser, but you get better quality, I guess is what I'm saying, if you create a PDF. And so that's what I ask you to do on the assignment, is print a PDF. One thing I'll mention is if you don't zoom extents, then your print is going to be a smaller part of the screen. So for example, if I was just zoomed out like oh, that's too much. Let's say I was zoomed out like that, and now I do the print preview. My print preview is going to be a smaller part on the page, like that. So when it's in this scaled mode, it's important for you to do the zoom extents button so that your model is filling up the window, your drawing window, and then you will get, oh, not set up. Then you'll get your print to fill in the majority of the printing space that's available. It's not perfect at it, but it does better. It's 12:48. We're out of time. So just a reminder, like this demo has been recorded, so if there's a certain part that I went through too quickly, you could watch it later, or if you forget between now and when you do the assignment, you can watch it later. And feel free to stop by if there's something I can help you figure out. You can stop by my office, or you could give me a call on Teams and share your screen with me. I'm more than happy to help you out. So let me give you this homework assignment, and that is it for today.